Hey, it's Kyle again, and I'm going to talk about deriving differential equations for a cooling tower. So I'm going to describe the cooling tower we have real quick. We're defining position z equal to 0 of the cooling tower at the top, and the positive z direction is going down the cooling tower. We have a flow of water going in the top, and we're going to call that a liquid flow L, and the unit on that is going to be kilograms per area per second. We also have a gas flow going in the bottom and out the top of the cooling tower, and we're going to call that gas flow G with a unit of kilograms per area per second as well. As I showed here, we have a packed cooling tower, so we have this specific area of meters squared per meters cubed, and we have the cross-sectional area of the cooling tower as big A, which is just meters squared. So the first differential I want to take a look at is the change in mole concentration of water in the gas flow with respect to position. So first on the left, I want to think about what's changing. So as I've stated, it's going to be this gas flow rate and the water concentration in it. And to get it into moles per second, we want to multiply by the cross-sectional area over molecular weight. So now we want to move to the right side and think about what's actually causing this change in concentration. So it's going to be mass transfer. So we have the mass transfer coefficient Kc times the difference in concentration that's causing it, causing the mass transfer. And we have our specific area and the cross-sectional area times the change in position, and what that's doing is kind of showing that the change is occurring as the flows are going through the cooling tower. So now we're going to be seeing this term a lot here, so I kind of want to define this as its own thing so I don't have to keep rewriting that, and we're going to define that as the molar flux of water. So, as we have seen before, we can actually define concentrations in terms of partial pressures. So, down here, we are going to define that as the partial pressure, and the partial pressure at the interface is just the saturation pressure of water at that temperature. So, water TW, saturation pressure over RT, and then RT, and then the concentration of water in the air is going to be the total pressure. Oh my gosh. The total pressure over RT, and since we want the concentration of water, we want to multiply by the mole fraction of water in the air. So that we can think of that as just that term is the molar flux of water. So now we have this area, cross-sectional area term on both sides that we can cancel out. And then we can draw the constants out of the differential. So we can assume that the gas flow rate and the molar weight, or molecular weight, are constants. So we're left with gas flow rate over molecular weight times the change in concentration on the left side, and on the right side we're left with this molar flux times the specific area times the change in position. And now if we want to take a look back at the cooling tower itself, we can see that we have this gas flow rate that is going in the bottom and out the top. So as the gas goes in, it's going to be at a lower concentration of water, and it's going to pick up water as it evaporates from the liquid stream into the gas stream. And it's going to go out the top, so it'll have a higher water concentration when it leaves versus when it enters. And since we defined this position z equal to 0 at the top of the cooling tower, we actually are going to need to throw a negative sign into this differential to account for that, because this differential will say it's going to say that the concentration of water is actually going up and increasing in the air, when in reality, with respect to the position as we defined it, it's really decreasing, because it'll be, as I said, at a higher concentration of water here at z equal to 0, and a lower concentration of water here at when z is the max. So we'll throw that negative sign in there, and now we have our differential, we just need to solve for it. So dy over dz is equal to negative a times the molecular weight over gas flow rate times molar flux of water. So that's our first differential. And now we'll move on to the second, the change in temperature of the water with respect to position as well. So whenever we see a change in temperature, we want to think of enthalpy. So change in enthalpy of the liquid, and that's going to be equal to the liquid flow rate times the heat capacity, since we're changing the temperature, and the actual change in temperature of the liquid. And then since we defined our liquid flow rate to be in kilograms per area per second, we need this cross-sectional area here. Then now we want to think about what's actually causing this change in temperature. So there's two things, the heat transfer between the air and the liquid, and the evaporation of water, which actually decreases the temperature of the liquid. So, as I said, the first thing is the heat transfer with this driving temperature, the difference in temperature of the gas and temperature of the water. And then we again have this area times volume. And as I said, the evaporation of the water will actually decrease the temperature, so minus. And since water is evaporating, we need the heat of evaporation times the molar flux of the water. And again, we have this area and specific area times the volume of the cooling tower. So now, again, we can see we have this area and all the terms that we can cancel out. And then we can isolate the change in temperature over the change in position, and we have our differential equation. So we have change in temperature over change in position. Oh. And on the right side, we have a common term of the specific area in both terms, and then we have this liquid flow rate and the specific heat of the liquid. So we'll combine those. You know, the A is multiplied, and these are going to, once I divide these onto the other side, it would be in both terms. So liquid flow rate, specific heat of the liquid. Then we just multiply this by what's left. So we have the heat transfer with the temperature difference. Gas minus temperature of the water minus the enthalpy of vaporization times the molar flux of water, and that's our second differential equation. And now we're going to take a look at the third differential equation. So that is another change in temperature, except this one we're going to look at a little differently. We're going to look at kind of a section of the cooling tower, so that'll be dz. So we have this liquid flowing down, gas flowing up, and they each have their enthalpies. So since we know the cooling tower is a closed system, we know that all the enthalpy in it is going to remain, and the difference, the actual change in enthalpy of the liquid and the gas at different positions is going to equal 0. So what we can see from this is that the change in enthalpy of the liquid is going to be equal in the change in enthalpy of the gas. And now that'll help us solve for this last differential equation we have. So if we want to think about the enthalpy of the gas, we have, similar to the liquid, we have this area times the gas flow rate times the specific heat of the gas times the temperature of the gas. Then this time we have added the heat of vaporization, so we have lambda for the heat of vaporization, and again we have area times gas flow rate. And since we want the water in the gas flow rate, so mole fraction of water over the molecular weight. And then, as I said, the differential of that is going to be equal to the differential of enthalpy of the liquid, which, am I running out of room, maybe? is this equation we have here. So the heat transfer coefficient times temperature difference times the area and volume, and then minus the lambda molar flux of water. Okay, so now if we kind of start to take away like terms, we can again cancel out these areas and everything, and then we can actually see that the constants are involved as well. These are constants. These are constants. So when we divide the change in position over to this left side, I think I'm running out of room. I'll move over here. So we're going to bring the dz onto this left side. So we're left with, alright, yeah. So we're left with the gas flow rate times the specific heat of gas. And then we have the things that are not constant, dz. And we have this this term as well. So plus the gas flow rate, and we have dy dz. I'll erase this a little bit. It's getting in my way. And we're going to set that equal to the left side, which we brought dz over, so we no longer have that. So now we just have what's left over there, which is specific area times the heat transfer coefficient. This is change in temperature. Minus what we have left there, which is lambda, water, specific area. And now if we look on this left side over here, we actually have this first differential we solved for. So if we look at what we got for that one, we can actually cancel the m and the g, because we have g over m, the gas flow rate over molecular weight here. And this one we have the inverse, so we can cancel those. So we're left with minus lambda from here, specific area from there, and molar flux of water from the other differential. And if we look at this term, it's actually the same as this term, so we can cancel both of those out, which that comes in handy. And then what we're left is we have the differential that we want, and we just isolate that. Where do I have room? I can kind of write that neater down here. So we have the change in temperature of the gas with respect to position, and we have that equal to, this term's gone. So now we move the gas flow rate and the specific heat of the gas to the right side, and we have the specific area times the heat transfer coefficient over gas flow rate times the specific heat of the gas times this temperature difference. And that is our third differential. I don't know if the video kind of caught that bottom, but that is what the third differential looks like right there. Next, I will be coding using Python to help solve these differentials with a real world application with numbers given for the flow rates and everything like that. So that'll be the next part of part B for exam 3.